Hi everyone! We're going to continue on with question 4.5. We were here at our last time that we talked in our PowerPoint notes. This question was a force F acts on mass m for a time interval t, giving it a final speed v. It says that the same force acts for the same time on a different mass, 2m, so we're doubling mass. What would be the final speed of the bigger mass? So we started to work on this in class. I think most people agreed that the answer was D. It would be half the speed for the final speed if I double the mass. So force F acts on mass m over a time interval, giving it a final speed. So ultimately, I know that velocity and time are related to velocity and time are related to acceleration, in that I know that force is equal to, go here really quick. So I know force is equal to mass times acceleration, and I know that acceleration is also equal to a change in velocity over time. So really, force is equal to mass times this change in velocity. Let's assume it started at rest and then had a final speed over time. Okay, so same thing. I just substituted this in here for A. And they told me that I'm going to apply the same force, but now I'm going to double the mass. 2m times v over t. What would happen to the final speed, or what would the final speed be like? So all I want to do is rearrange what I've just done here, but now for v. So if I do that, I would have multiply both sides by t. So let's actually go this way. So I would have force times time equals 2mv. Then let's just get v by itself. So let's divide this by 2m. So then I'm just left with v equals ft over 2m. Or ultimately what I'm seeing is half of this. So ft over m is what I would have got for just that normal one, but now because I've doubled mass, what I've done now to my speed is that it has changed by a half. So it's really 1/2 times then that quantity. So that's the reason that D is the correct answer on this particular question. So it should be 1/2 V, okay? The next few multiple choice questions here, what I'd like you to do is I'd like you to answer them on a separate piece of paper, because we're going to go over what your answers, what you think the correct answer should be. So make sure that you either write notes about what the question is, make sure you draw the picture so that way you understand what it is. So it says a force F acts on a mass m1, giving it an acceleration a1. So I have this force acting on block 1, we'll call that m1, and it has an acceleration which we'll call a1. The same force, so here's my same force that we applied up here in this first one, is going to be applied to a different mass. We'll call that m2. And now it has an acceleration a2, but really the same force given or applied to this mass m2 is really just double acceleration number 1. Okay? So same force is applied to both m1 and m2. And m2 is twice the acceleration of the first one. Same force though. It says if m1 and m2 are glued together, so like I see down here in the bottom one, so it goes m2 and then m1, and the same force acts on this combination, so same force is in all three, what is the resulting acceleration? So A is that you have 3/4 of the first acceleration, B is 3/2 times the first acceleration, C is half of the first acceleration, D is 4/3 of the first acceleration, or E is 2/3 of that first acceleration. So I want you to try to come up with what answer you would choose and show me mathematically why you would agree with that answer, okay? Next question that I want you to look at, if you push with force F on either the heavy box M1 or the light box M2, in which of the two cases below is the contact force between the two boxes larger? So on this side on A, I have a force that's pushing on the smaller mass, M2, and then that smaller mass is attached to a larger mass, M1. Versus in the other option, I have the force applied to the larger mass, M1, which is then going to push M2. And my question is, in which case is the contact force would be between M1 and M2, in which case, A or B, is the contact force larger, or is it the same? So show me, either mathematically or with symbols, why you would think it would either be A or B or the same. Okay, let's talk about Newton's third law. So we know that Newton's first law is that for an object in motion will stay in motion and an object at rest will stay at rest unless it's acted upon by an external or an unbalanced force. Ultimately, our goal then is to cause an acceleration. So Newton's second law is that acceleration is directly proportional to force while being inversely proportional to mass. Newton's third law states that for every force or for every action, there should be an equal and opposite reaction, or an equal but opposite force. All forces occur in pairs. That's what Newton believed, that all forces occur in pairs. So this notation writing, the way that you see it here, I have the force of object 1 on object 2. And that's equal to the force of object 2 on object 1. So the way that we write it is, this is the force of 1 on 2, and this is the force of 2 on 1. Okay? That's how that reading will go. They should be equal in magnitude, but they should be opposite in direction because of these pairs. So it says that note that action and reaction forces act on different objects. We're not talking about the same object. So for example, I have a wooden block here, and it says that I know that there's a downward force that's acting on the table. And I know that that downward force is being exerted by that wooden block because it's the block's weight. So mg is just representing my weight force here. Okay? So mg is just representing my weight force. This block is pushing down on the table, but the reaction force is going to be the table pushing back up on the block. So your forces that occur in pairs are going to be off of two totally different objects. So action-reaction forces act on different objects. That's a really, really, really big misconception with Newton's third law, that we believe that since the forces occur in pairs, they should be occurring or originating from the same object, but they don't. So this is just an example, really simple example. The weight of the block is the action force, and the reaction force would be the table pushing back up as the normal force on the block, okay? So another multiple choice question, let's do this one. A very large truck sits on a frozen lake. Actually, this is kind of a throwback to Newton's first law and second law almost. A very large truck sits on a frozen lake. Assume that there is no friction between the tires and the ice. So we're assuming a frictionless environment here. And plus, let's assume it's on Earth. A fly suddenly smashes against the front window. What will happen to the truck? A, it is too heavy, so it just sits there. B, it moves backward at constant speed. C, it accelerates backward. D, it moves forward at constant speed. Or E, it accelerates forward. So I want you to come up with which one of these you agree with, and then give me a reason as to why. I want you to justify this. So we have 3 that we have to justify at the beginning of class. And actually, I know that Friday, I don't know how long the senior breakfast will take, but let's say that you get back with half of class left. We're going to start off with these here, and then try to finish up the homework problems and going over those, okay? So Newton's third law, this is just kind of exhibiting some action-reaction forces, and this is just for someone carrying a briefcase. So if I'm looking at part A, I have at a distance forces. So these would be my at a distance forces. I have the weight of the briefcase, and then I also have the attraction of the Earth, specifically that's trying to pull that briefcase more toward it. So action-reaction forces could be here. But I also have another contact force because I have this lady is holding or pulling up the briefcase. So she's pulling up on the briefcase. So there's a force based on the muscles that are in her hand to pull it up. Just like there are forces on the briefcase trying to pull it down towards the ground based on the weight force. So these are equal and opposite, and then the at a distance forces between the weight and the Earth here of the briefcase are at action-reaction forces. But here's a question that I want to pose, come up with a reasoning, and then we'll discuss this one too on Friday. On B, she drops the briefcase. I no longer have this contact force. What are the forces? What is the action-reaction pair in B? And is there one? Or is there just one force? Or are there action-reaction pair? Tell me. So you justify what you think the forces would be after she's dropped the briefcase. Okay? And then we'll discuss. So let's get into utilizing Newton's second law. There are certain problems that you're going to see more often than not in terms of Newton's second law. One of those things is going to be called a translational equilibrium problem, meaning that something is at rest, or it's moving at constant speed. So there's no net force acting on it, which means that if we're writing an equation, net force is just going to be equal to 0. So if an object is in translational equilibrium, there must be no net force on it. So this means there's no net force in the x direction, or there's no force in the x direction, there's no in the y direction, and there's none in the z direction. So this chandelier hangs at rest, and it stays at rest because the tension holding it up in this cord to the ceiling is equal to the weight force of the chandelier. So we would say that this is in translational equilibrium. Well, how do I go about solving problems like this? We're going to do a couple of these. This first one says, a force of 10 newtons is applied at an angle of 30 degrees to the horizontal on a 1.25 kilogram block, initially at rest on a frictionless surface. And I'm asked two different things here. First of all, I'm asked, what is the magnitude of the block's acceleration? And then the next question I'm asked is, what is the magnitude of the normal force? Okay, so it says that the block is initially at rest on this frictionless surface, and then I'm going to apply some type of force. So this is actually not even a translational equilibrium problem at all. Just kidding. This is going to be an acceleration. I may have a net force problem here, okay? This is how I want us to set up all kinds of Newton's second law problems. I need to think about the forces that are acting in the x direction, and I need to think about the forces that are acting in the y direction. So specifically, draw a free body diagram. That's my first goal, free body diagram. So I know I have a force of 10 newtons. I have some horizontal surface, and I have some block, we'll just call that mass M, and a force is being applied 30 degrees to the horizontal. So maybe it's just being pulled. So here's my applied force. And I told you that that had a magnitude of 10 newtons. And then it's being pulled at an angle of 30 degrees. So that's my picture. Let's represent a free body. So I know it has a weight force. I know it has a normal force, and then I know it has this applied force, which we already know is 10 newtons. And then that's at, which is a really large force, sorry, that's at 30 degrees. So there's my free body diagram. The first part of that question asked me, what is the magnitude of the block's acceleration? My goal is to find what acceleration is.